We're ready to talk about Chapter 6, and 6.2 is the standard normal distribution. Now, in Chapter 5, we talked about different types of probability distributions or the basics of a probability distribution. We said that it could be given to us as a table, and in the left hand column, we would have all possible outcomes of an event, and in the right hand column, we would have the probability associated with each outcome, and all those probabilities had to add up to 1. In Chapter 6, we're going to talk about normal distributions and specifically the standard normal distribution. But let me just mention a couple other types of distributions to you first. We've already mentioned these other types in section 2.3. The first is a uniform distribution where different possible values occur with approximately the same frequency. And I gave you this graph of the frequency of the appearance of digits in the first 3 billion digits of pi. In the first 3 billion digits of pi, there are the same number of zeros as there are ones, as there are twos, all the way up to the ninth digit. So you could say that the digits of pi are uniformly distributed between 0 and 9. We've also talked about a normal distribution where frequencies increase to a maximum and then decrease at relatively the same rate at which they increased. The graph is symmetric with respect to the center of the graph. The left half of the graph is roughly a mirror image of the right half. And an example of some scores that are normally distributed are IQ scores. The average of IQ scores is 100. It's right there in the middle, and the IQ scores are distributed about the same below the mean as they are above the mean. A uniform distribution may be used to illustrate the relationship between probability and area. Now, you have a problem like this in the homework. You're calculating the probability for a uniform distribution. For a New York City weekday late afternoon subway travel from Times Square to the Met Station, you can take the number 7 train that leaves Times Square every 5 minutes. Once arriving at the Times Square station, your wait time for the number 7 train could be anything between 0 minutes and 5 minutes, and every possible wait time is equally likely. Is wait time a discrete or continuous random variable? Well, to answer that question, just remember discrete random variables represent values which result from counting, and continuous random variables result from values which are measured. Since time is a measurement, wait time is a continuous random variable. The probability that your wait time will be between 0 and 5 minutes inclusive is what? You arrive at the station, there's a train coming every 5 minutes, so you're guaranteed a wait time between 0 and 5 minutes. Either a train is ready for you as soon as you get there, or you may have to wait up to 5 minutes, but certainly your wait is sometime between 0 and 5 minutes inclusive. That means the probability is 1. The probability of any given wait time can be represented by this rectangle. Your possible wait times are anywhere between 0 and 1. That gives you the length of the rectangle. And you can think of the rectangle as consisting of 5 smaller rectangles if you break them down into 0 to 1 minutes, 1 to 2 minutes, 2 to 3 minutes, and so on. What would the height of each rectangle have to be in order for the total area of the rectangle to be 1? We said the probability of a wait time between 0 and 5 is 1. So what would this height have to be if this entire rectangle was to have an area of 1? In general, for any rectangle of length L and height h, if L times h is going to equal 1, if you solve that equation for h, then h is going to have to be 1 over L, or for this rectangle of length 5, for that entire rectangle to have an area of 1, then the height of that rectangle would have to be 1/5. 1/5 times 5 gives you 1. So we have a rectangle that is 5 units long and 1/5 of a unit tall, and the area of that rectangle is 1. To find the probability that your wait time will be greater than 2 minutes, that's the area I have shaded here, a wait time between 2 and 5 minutes. Well, the length of the shaded portion is the difference between 2 seconds and 5 seconds. So the length, or in this case, I'm calling it the width, is 3 seconds, and the height we've already established was 1/5. 1/5 times 3 is 3/5, or written as a decimal, that would be 0.6. That means the probability that your wait time is between 2 and 5 minutes inclusive is 0.6. Now think about that. The exact halfway point between 0 and 5 minutes would be 2.5 minutes. So there would be a 50% chance that you would wait less than 2.5 minutes and a 50% chance that you would wait more than 2.5 minutes. If we bump that back to 2 minutes, there's only a 40% chance that you'll wait less than 2 minutes and a 60% chance that you'll wait more than 2 minutes. But that shows you that the total area under the curve between 0 minutes and 5 minutes is 1. Those two probabilities add together to give you 1. Just as we have seen that the probability of a given outcome for a uniform distribution can be represented by the shaded area of a rectangle, the probability of a given outcome for any distribution can be represented by a shaded area under a curve, so long as the area under the curve is 1. The area of the rectangle was 1, the area under a normal distribution is 1. We can use this concept, for example, to find the probability that a randomly selected pregnancy lasts between 238 days and 298 days if we know that the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. For every problem that we do in this chapter, we're going to draw a normal distribution. In this case, the mean, which is always in the middle of the normal distribution, is 268, and standard deviation is 15 days. We're going to talk about how to find the probability that a pregnancy lasts between 238 days and 298 days. So we'll be looking for the probability that a pregnancy is complete somewhere in this shaded area between 238 and 298. Now we're going to talk about how to find that on the calculator, but think about something that you already know. How many days is 238 from 268? Or how many days is 298 from 268? They're both 30 days from the mean. And how many standard deviations would that be? Well, if one standard deviation is 15 days, then two standard deviations is 30 days. In other words, the 238 is two standard deviations below the mean, and the 298 is two standard deviations above the mean. What percent of the population do we know lies within two standard deviations of the mean, either two standard deviations above or two standard deviations below? It's the empirical rule that has already answered that question for us. If we know that we're looking for the probability that in a normally distributed population, a value lies within 2 standard deviations of the mean, that probability is 95%, or expressed as a decimal, 0.95 by the empirical rule. What if we weren't talking about exactly 2 standard deviations, or the empirical rule would even give us the probability for 1 standard deviation or 3 standard deviations? But what if we wanted a probability of something being, let's say, 0.736 standard deviations from the mean? How would we find that? Well, that's the task of the day. In 6.2, we're specifically talking about a very specific type of normal distribution called the normal distribution. And the normal distribution has 3 properties. Number one, it's bell-shaped. All normal distributions are bell-shaped, so that's not special. But its mean is equal to 0 and its standard deviation is equal to 1. Now, there wouldn't be very much raw data in the world that would be represented by a standard normal distribution. Think about it. If the mean is going to be 0, then there would need to be the same number of values below 0 as above 0. They would all have to average out to 0. There's not very many real life data sets that are going to have as their average of the values or the mean of the values 0. So there are limited applications of this, but it allows us to talk about normal distributions which are not standard in section 6.3. The 2 things we're going to do in chapter 6 are we're going to find areas or probabilities. Probabilities and areas are synonymous. Find areas or probabilities corresponding to various regions under the graph of the standard normal distribution. In other words, for all the word problems, we're going to draw a standard normal distribution just like the one that I just mentioned, and we're going to be given some left score and some right score, and we're looking for the area between those 2 values, or the probability that a value lies within that range. The second thing we're going to do, if I give you the area, then I can ask you to find a z-score. For example, I can give you that the area to the left of this score is maybe 0.4 and ask you to find what that score is. And those are the only 2 things we're doing in all of chapter 6. Again, the standard normal distribution is a normal probability distribution which has a mean of 0 and a standard deviation of 1. The total area under the curve is equal to 1 because all of the values are going to lie within some number of standard deviations from the mean. We could go all the way out to 10 standard deviations below the mean and 10 standard deviations above the mean, but the empirical rule tells us that 99.7% of all values lie within 3 standard deviations of the mean. That's almost the complete area of 1 lying just between z-scores -3 and +3.